Good morning, leaders. A very warm welcome to all of you to yet another training session called Transformers, the base for LLMs, organized by NHKE. So, without any further ado, we shall get started with the session. And a quick introduction of today's speaker, who is Abhinav Sharma. Abhinav is a data scientist who has about 4 years of experience in the corporate setup. He is currently serving Brain as an associate solution leader in the Grammar team. Coming to his expertise lies in computer vision, natural language processing, and graph machine learning, to name a few. He's passionate playing guitar, hitting the gym, trekking, and outdoor activities. Having introduced Abhinav, I would like to hand over the stage to you. All over to you.
Yeah, thank you, Suman. So, good morning, everyone. As Suman mentioned, my name is Abhinav, and today we'll be covering transformers, which is the base for your many popular deep learning models such as BERT, GPT-3, and yes, even the current Chat GPT. So, the transformers module was basically invented in 2017 by Google. And when it came, it actually created a storm in the NLP field, such that it down route dominated all the NLP benchmarks. But let's just see what was there before transformers and what was the problem with that, with the previous state of the art techniques. So previously, for any NLP task, that is encoding your text into some kind of information, we were using some for loop kind of mechanisms of deep learning, such as LSTM, RNNs, or GRUs. But there were two basically main problems with those architectures. One is that it decoded information sequentially, that is at the inference time or at the prediction stage, everything that was coming there was all happening one by one step at a time. So naturally, the inference was slow and it was very difficult to scale them. Second thing is for long sequences, they were not actually much viable. So in terms of if I say something like a machine translation task wherein you're translating from one language, say English, into another language, say Hindi. So into Hindi, what was happening was the quality of the translation was getting reduced as the sequence length or the number of words in the source sentence was increasing. So clearly there was a need for a new architecture over there. So let's just go through how LSTMs actually encoded and decoded things. Let's take an example of machine translation only. For example, if I have to do something like translate I am a Abhinav to मैं अभिनव हूँ. So how LSTMs would work is they would take in a token over here, which was any start of sequence token over here. They would take in they would take in the current token, which is I over here, and they would generate some embeddings on top of it, which we called cell states and hidden states. So think of that signal as like this of fixed length. Okay, this signal is fixed length. So what happens is this signal is propagated into this token. So now this I, which is being encoded into some matrix, will be targeted into the next cell. And this cell will now get the context from the previous, which is I, the current context, which is am, and then it will encode it into some signal. So let's just say the length of the signal will remain the same. So now the signal will become like this. It has information of two tokens. Okay. Now, what happens again is this signal is again propagated forward into this cell. And then again, the signal is then again compressed. So let's just signal length remains the same, but the information available to this token of the previous token is just getting compressed. Okay, it should be red. And then the new information, green. So this mechanism continues on for n sequence length. That is, if you have n tokens. So as so clearly the con is that as the sequence length will increase, the amount of information which is available to the current token of the previous token will keep on decreasing, which is why LSTM acts as a compression algorithm, and which is why it was not that great for big sequence length. And then coupled with its for loop kind of mechanism where you have to feed in the previous sentence state and the current token every time. It's a for loop kind of, it's sequential, it's for loop, and we all hate for loops, which is why it was very slow at the training time. And that is why there was actually a very potent need of transformers. Let's just go over the architecture and let's just see what changes did the transformers make. So actually, this is an LSTM, and this part over here is inside the LSTM. There's bunch of complicated machinery over here that we don't have to worry about. Just this higher level overview is enough for the scope of this session. Okay, because we'll be diving deep into transformers. So now let's just see. Okay, so this is the full architecture of the transformers, and it has basically a couple of core modules in it. So firstly, this part over here, this part over here is what you called a encoder, and this part over here, this part over here is what you called a decoder. Okay, so essentially, the job of the encoder is to transform an input x into x prime. X prime can be anything that we do not understand, but the model has some sense of it based on the problem it is targeting. Say, for example, you're targeting image captioning, right? Image captioning. So in terms of image captioning, this is an image, and this becomes some matrix x prime. And then this x prime is taken by the transformer and feed it into the decoder, where it can, given the context of the image which it gets from the encoder, context of the image, it tries to caption that image, caption that. It can So it can be anything actually. You can even encode text, images, audios, anything. Transformer architecture has shown to be very universal in the way in terms of its algorithm. Okay, so transformers actually implements a few core modules, which was different than the rest. First thing is this positional encoding. Second thing, and the crux of the architecture, this attention. Third thing, another new thing is the layer normalization, layer norm. And then fourth thing is this masked multi-headed attention, masked multi-headed attention. And lastly, this module called cross attention. Okay. So let's dive deep into all of these different modules, and let's just see how the journey of a sequence inside the transformer is. And we will be taking an example for all of this. So let's just create a dialogue completer. Okay. It is from the game. The code is from the Game of Thrones, and it's very famous. The input is when you play the Game of Thrones, and the transformer should complete this code. Okay, so ideally, what you would do is there is your there is your deep learning or machine learning model that is trained on all the corpus of the dialogues of this Game of Thrones dialogues, and whenever it sees this prompt, when you play the Game of the Thrones, it should just output whatever is next. So I'll just complete it. When you play the Game of Thrones, you either win or you die. Okay. So this is the input when you play the Game of Thrones. But this is how we understand it. How can a transformer that doesn't know anything about words or anything understand it? And how do we even input this sequence into the transformer? So We do it by creating a matrix out of that sentence. So it doesn't understand the words, but it understands matrices. Transformers operate in 3 dimensions as a tensor. Okay. Let's just go ahead. So, actually creating that sentence into your a matrix is actually very easy. So, suppose you have a vocabulary of all the words. Okay, you have the vocabulary of all the words, and then what you basically do is you create a dictionary such that each word is assigned an index. It can start from zero and it can go to anything up to your unique token words. So in this scheme, what happens is once you do this, what happens is you replace each word with the indices that you assign. So for example, you can see that when is assigned 2458. So we replace when by 2458. Similarly, u 5670 and all of that. So now we have something that the transformers can understand. But it still doesn't know the meaning of this word because they are just indices. And for anything we do that is language related, we must know the meaning of the words, right? So what transformers actually does is when this input is tokenized, it is sent into this input embedding layer. This input embedding is nothing but a trainable matrix. It's a trainable matrix which is a torch.nn.parameter layer. Okay, and this is nothing but a giant 2D block wherein each indice is just mapped to some vector of word. So let's just say right now we are embedding each token into 5 features, 5 dimensions on 5 features. Okay, this is just a hyperparameter. The original transformers model actually used the 512 dimensions. The intuition behind basically transforming them into more than one dimension is that we basically think that each of these dimensions are capturing some of linguistic feature about that word. So, for example, maybe linguistic feature of play, feature one can capture that it's a verb or something, that it's in this tense or it's in that tense, but we don't know what it's capturing. This is just our headcanon. This is just what we are thinking, and actually decoding what these things mean. It's actually non-trivial. Means it's very hard, and mostly it's not even that beneficial for us. Okay, so essentially you just passed all of your token at once into this embedding layer. It fetches by the indice, it fetches all the 3D matrix of X, whatever it is there, and then it transforms it into these numbers that we like. Okay, this is what you call a word embedding, and these are all trainable. These are all trainable. Forgive me for my writing. I'm very bad at this. So anyway, these are all trainable. And what actually happens when you train a model for these word embeddings is that the phenomena that happens is the embeddings. So you have 5 features over here, right? So there are some machine learning algorithms such as tsne or umap or anything that transform these 5 features into two features such that you are able to now plot it on a graph such like this. So the interesting thing that happens is the embeddings are uh, of such high quality that words like king and queen, when you plot it against words like apple and mango, they are so these words are closer to each other because there is some sense of relationship over there. But these words are then far away from these other because the relationship there is it's very unknown over here. The king can eat an apple, but king is very similar to queen in the terms of its power, authority, and everything. So these vectors are all they get the inherent meaning when we train them in such a manner. Okay. So now what we have essentially done is LSTM was taking things one at a time, and it was also compressing the signal, right? So for example, for this word, all of these words would be so small. There might not even be any information left when you want to attend from this token to this token. But what transformers has done is it has taken this input all at once, and it has encoded it into some form of embeddings which are trainable, and it all happens at once, or our favorite word parallel. So this is a parallel pathway over here. Okay. So now we know the meaning of each word. What is left? Uh, so now we know the meaning of each words from our input embeddings over here. But if you really think about it, all of this over here, we actually, the transformer does not know the position of them because all of this is taken at once, right? This and over here. So when you play the Game of Thrones, the Transformers embeds everything all at once. We don't know the position of the word, like which token came first, which token came last. And you might be asking, why does it even matter? Why does the order even matter? Actually, it does matter, and it is of absolute significance for us. Just you can just get the intuition of it just by looking at this example. So even though she did not win the award, she was satisfied. This not over here says that she did not win the award, but she was satisfied. So overall arching theme of this sentence is in a positive sense, because she was satisfied at the end, maybe by her hard work or whatever. Now, in the second sentence, if you just replace this not over here, even though she won the award, she was not satisfied, maybe due to something or something. So, the overall arching theme of this sentence has now become slightly towards negative. So, what can we do to mitigate this problem? Can we just add, say, like zero? Okay. Can we just add, say, like a 0 to this, a 1 to this, a 2 to this, a 3 to this, 4, 5, 6? Can we just do that? Actually, if you look at these embeddings, you might be seeing that these numbers are very small. So if we add positional embeddings of this magnitude, and it only goes worst when you go towards 512, which is the original dimensions supported by the transformer. This positional embedding will just basically be the dominant, play the dominant part over here, and all of these vectors that we gathered will become meaningless. So then what else can we do? Can we say that, can we add fractions? So say like what? Hmm. Can we add some fractions? Say like 1 by 5, 2 by 5, 3 by 5, 4 by 5. Okay, 6 on a tree. 6, 6, 6, 5 by 6, and 7 on a tree. Okay. Whatever. Fractions. Can we just add fractions over there? Uh, because that would actually make them pretty small and comparable to these numbers over here. But even that is a problem for the transformer, because if you add it in this way, suppose you right now you have 7 words, but then you have, let's say, 20 words. So the fractions will change. 1 by 20, 2 by 20, 3 by 20, and it will keep on changing for n sequence length, right? So what what we think is that when you keep on changing this thing, the transformer is actually not smart, it is quite dumb. It will just get confused about what are you doing every time you are giving me different things. So that is how so even this is not a viable option for us. But can we do something even better? What do you guys think about frequency? Yeah. Let's say what frequencies. something like this, and it goes on. Hmm. Yeah. Okay. So, okay. Zero, then zero, in, then one. So if you just represent them as this kind of frequency, you can see that this you can see that this part is oscillating after every position. This is oscillating after every two position. This will oscillate after every four position, and this will oscillate after every some x position. But I've done quite a lot of reading, and this is not how they represent the frequencies over here. Maybe because because all of these are floats, and you'd have to in vain you'll have to convert all of these to floats, and then it would be a headache to store also. So what the peeps over there at Google did is they created this function where they encode the positive dimensions by using sine, and they encode the odd dimensions by using cos. So sine and cos are actually opposite of each other. So when the sine is here, the cos will be here always. Okay, so what actually happens with this is you can see that the formalized sign of POS, this is the position of the token. So over here it would be 0, 1, 2, 3, 4, 5, 6, or rather 1 over here, 2, 3, 4, 5, 6, and 7. So what actually happens is if you actually look at this D model is the dimensions of this feature vector. So we have taken 5 over here. So D model will be 5. In the paper, they chose 512 because it was 512 of the size of the embeddings, which is this. Embeddings is this. Okay, so what actually happens is as the position increases, this number gets smaller and smaller, and the okay, let me just erase it again. What actually happens is the token at position 1 will only maybe oscillate like this. The token at position will 2 might oscillate like this. The token at position 3 might oscillate even faster, and so on. So basically by the number of frequencies of each token, the transformers module are able to identify the position of that token. So suppose, and since this is irrelevant of the number of words, this remains a constant, and hence the transformer model will not get confused with all the different types of sentences that we have. So let's just plot it and let's see how it looks like. By the way, how you add it is it's just a whatever embedding you had, whatever embedding you had, you just sum it up with the positional embedding, which is this one. Cool. Let's just plot it and look at how it sees. So I've plotted for different positions. So at position 2, 3, 4, 10, and 20. So if you just look at the position for 20 and 10, how the behavior is, it's something like this. This, this, and then it takes its final values between 1 and 0. But if you look at position 20, which is very clearly visible over here, how it goes is it goes like this, then it does this M thing again, and then only it finally converges into this area. So this was just the visual guide of how the positional embeddings looks like. So the higher the position you have, the more the numbers will oscillate, and the more the numbers oscillate, the more they retain that it's a word that is at a higher position and not a lower position. We can actually zoom in and let's just and see. So even So this is the purple curve. It is doing this. Then it again does this. Then it finally goes over here and it starts converging. But something such as at position 4, what it's doing it is just does this, and then it goes on to taking its final values between 0 and 1, which is the final values of sine and cos. Cool. Any questions here? None? Okay, we'll move ahead. So now, till now, we are able to find the meaning of a word and we know the positions of the word. What comes next is this vector, which is meaning plus position of some length. For example, in our case, it's 5. It's 5. This now is replicated 3 times, as you can see in this diagram over here. This is replicated 3 times. Okay, and now this is sent into multi-headed attention module. So this is actually the main part or the crux of this transformer module. And once you split this, the transformer architecture calls it key, query, and values. Okay, so that's just what they call it. Let's just go into the slides. Yeah. So let me just give you an intuition about attention. So attention is even if we as humans are doing a task, suppose we are learning about some bank finance things or something about cricket, we might pay attention to some words and we might retain them in our memories such that they are in the important words that we need to understand and we need to take care more of. Right. So that's actually the idea behind it. Attention is also the algorithm is such that given a sentence, it focuses on the words which are most likely to answer your question. Right. So who is this Game of Thrones character is the question, is my question. And this is the context that I have been provided. She faced her enemy and whispered Dracarys. So this is again a Game of Thrones reference. So, which I pay attention to she, enemy, and Dracarys. Okay. So with this she, I know that it's a female, and with this Dracarys, I already know that it's Daenerys Targaryen, the main lead of the show. Okay. But this is what you call as simple attention that has also been used in LSTM. What's different with transformers? So transformers, what it does is it incorporates self-attention. Self-attention. So what self-attention basically means is it's basically kind of introspection. You try to understand who am I, what are my qualities, what are my downfalls, etc. So for example, if I remove this word, if I just mask out this word, and if I just read it, he went to the dash and learned of his empty account. So if I pay attention to this empty and account and this vent, this is indicating to me that it is some sort of entity. And in terms of this entity, in context of this empty account, it can be bank, because you go to your bank or you go to your phone mobile app, you just look at what the information is and you finally realize. After which he went to the, if I mask out this again, he went to the river blank and cried. So now I need to pay attention to river. Went because he went somewhere. Cried maybe in the rain also. So, but river is there. So river bank is the most probable word. So this is basically the idea of self-attention. You do introspection of what you are, how you are, and what are your qualities. Right. So let's just so this is all the intuition behind the self-attention, but how do you represent this mathematically? So the peeps over at Google use something called as multi-headed attention. And this is basically the formula for this. It's You remember we diversified our embeddings into query, keys, and values, and we basically transform them by some linear layer into some x dimensions, and then we send it to this scaled dot product attention. And this is actually the formula for scale dot product attention. It's very similar. So let me just give you an intuition about query keys values. uh, so query is your question, right? Query is your question. This is what will guide you. What actually do I want from the contents that you have? Key value, you can actually think of it as a dictionary also. So given a question, you find the similarity, that which query is very similar to key, and then with that you basically retrieve its contents via value. So this is just a very basic high level overview of the scale dot product attention, and it's actually very simple if you actually look at it. It's just one formula, right? So just keep this image in mind. We'll be diving deep into all of these shenanigans. uh, yeah. So we called it self-attention. So, and we also said that input of the embeddings will be split into three values: query, keys, and values, right? So again, what you see here is the same sentence being said into the transformers multiple times. So one, two, three times. What actually happens is, so let's say we had five words, and we embedded them into seven words, and we embedded them in five dimensions, right? So the shape of the matrix is just 7 cross 5, where we have seven rows and five columns. So what we do then is we multiply them by some linear layer, which was there in the diagram. So we multiply all of them by some linear layer, right? So that is what being shown here in the diagram. We just multiply them by some linear layer, which is, it should be a square dimension over here, 5 by 5. So once you multiply this by this matrix multiplication, you get an filter of size 7 cross 5. What you have essentially done is, now you had the meaning of the words and all of that is fine, but now you need to map it to your current problem. So we need some transformation. Current problem. So we need some transformation that helps us do that. And this is the transformation that we do. We just multiply it by a linear dense layer, which is of shape 5 by 5 by 5 in our case, because we embedded into five dimensions. Okay. And then we get it transformed into another value of shape 7 by 5 only. So this is another that vector that we have. What I actually call it is just alignment. This is my intuition. Alignment towards uh, current problem, right? Because we know the meaning and everything, but we also need to understand, we also need to encode based on the current problem. So we go ahead. Now what we have done over here is, we have this part is complete, right? Now we need to feed this input into this scale dot product attention, which is nothing but this simple formula, right? So again, very simple. What you basically do is, you multiply. So query was of shape 7 cross 5, and key was also of shape 7 cross 5. What the formula of attention is, you do a dot product between transpose of k. So once you transpose it, it becomes 7 by 5 and 5 by 7. And once you do a matrix multiplication, you finally get something called an attention filter, which is of size 7 by 7. So this 7 by 7 size is very intentional, because we had seven words, right? We had seven words over here, and hence we have 7 by 7 filter, because each word needs to attend to each word and find out the importance of it with respect to the other words. So over here it could be when. Oh, okay, I have a next slide. Yeah, so once you do this, let's just zoom in on this one. This is how the attention filter will look like. And initially, without any training, these are all just random values over here. So in self attention, you have the same sequence here and the same sequence here. So now people also say that transformer is very data hungry. And just by looking at this, you can decode why that may be, because transformer actually takes in 512 words. So this matrix every time will be 512 by 512, which is a very large number to incorporate in your GPU, which has very less memory as compared to your RAM and is very expensive, right? So, which is why with the sequence length, the transformer's memory scales quadratically. 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 Okay. So initially, when you are training, it's just random values, but after training, you get some meaningful values. So let's just focus on this game over here. So this game, you can see that it pays the most attention to itself, but it is also paying very high attention to the word play and to the word thrones also, and to the word the. And so basically this is very context related attention, and whatever this value is, it is just a scaling mechanism. So this value actually states the importance of word with respect to each word. So for game, the most important word it itself क्योंकि मैं अपनी favorite हूँ, and then next thing is play, and then this thrones given the context. So essentially the formula, so these are actually very big values, but we operate in very small values, 0.02, 0.03, etc, etc. So what we actually do is we now scale all of this into a probability distribution, which is between 0 and 1, by our favorite function, which is called as softmax. So for each this row, this softmax is applied, and everything is now being converted into zeros, between zeros and one. And this is the final output that you get. This is a scaling mechanism inherently. Scaling mechanism. So if you look at our intuition behind query keys and values, query was the question. Key was the key was basically a key, and values was basically dictionary, where h- how does the outside of this question match with my query, right? And if it matches pretty high, I want the contents of it via value, right? So how do we do that? So when if we go back again, query keys and values were the same thing. Right. So what we have done is we have just gotten the score via this softmax of each word. So for example, given the current context, this throne has a very high value of zero point 0.8, or sorry, zero point 0.4. Then this game has a very high value of again zero point 0.4. And then this play could have 0.2. Right. And how do we get that? So this is 7 cross 7. And then basically then what happens is you have your value was 7, so the output of attention is 7 cross 7. You have your value, which is 7 cross 5. You do a matrix multiplication between them, and then you get the final value, which is 7 cross 5, which contains all the information about the tokens, which token is important given which token and which problem, right? So this is what I call scale dot product attention. But the people over there at Transformers actually implemented multi-headed attention, right? So this is just one attention. What they do is they in parallel they basically compute all of this in parallel each time. So basically, for example, say you have 8 heads. So it would be 8 cross 7 cross 5 over here. And each head would have the same input and would have slightly different output. The intuition behind taking multiple heads is that suppose there is one person doing one job, and suppose there are three-person doing one job. Uh, in most of the times or in most of the cases, what happens is three people doing one job will always be better because they provide a broader aspect towards the context, and hence they are able to better capture or pay attention to different things. So some information that might be missed by one head will be captured by another head or this head. So साथ ही हाथ मिलाला kind of thing है यहाँ पे, right? So all of this happens again in parallel. That is the theme of transformers. It's basically one gigantic parallel CU. Then you again transform this into something, and then you finally again get back your 7 by 5 vector, right? Any doubts here in attention? Yeah. Basically, because your question is something that you want to know about, right? So what actually happens is, based on your question, your keys and values are then aligned such that given the question, it retrieves the very context related key. And then you get the values of that key by using this value function, right? So this is actually the reason for query keys and values. And this is very scalable in terms of performance. And in terms of applying this technique, it can be applied to anything. Actually, currently in audio, even in vision, and even in graph ML and in NLP, transformers are ruling the world actually. So this is a very generic algorithm, and this can be applied to any problem that you have. You just have to formulate the input and the target variables, then this model will handle everything. Right. So we are done with this, the main crux of this algorithm. And let's just see what's left in transformers, which module is left. So okay, so now there was actually three copies, and this signal was transported from here into this add and norm. So what this is this is what you called as a residual connection. So if the transformer realizes that the computation of this attention over here, let me just make it a bit clearer. If it realizes or if it so chooses that, sorry, this information for the given task is useless, then it implements a residual connection, which is nothing but your this input, which I represented by x, plus the current x which you got after your multi-headed attention, MMA. So remember, the first shape of our embeddings was 7 cross 5, and then after attention also we got 7 cross 5, right? So what we do is we just simply 7 cross 5 plus 7 plus. We just add it. That's it. That's your residual connection. So what how you can think of add intuitively as a what information should I retain or what information should I take away, right? uh, or what information should I add? And then there is this norm over here. So this norm over here is not your normal batch normalization. Batch normalization is if you are sending 10 sentences, then it normalizes or it basically normalizes the distribution of all the values against this 10. But now in transformers, they incorporated something called as, okay, we just go ahead, called as layer normalization. So now instead of normalizing against your input, you normalize against this. Instead of doing against this, you normalize against this. The benefit is basically actually one fold only. So suppose you have trained something with batch normalization and it is trained on batch 10, right? Since you're normalizing against this 10 value, this can, if you change this in the inference time, then the normalization values will change and hence the model might output something which is worse than what you expected. So which is why the peeps at Google invented something called as layer normalization, where you basically normalize this against your features of every rows. Okay, let's just dive deep into it again. So what is actually layer normalization? It is nothing. So for example, if this row is x, then x minus mean of x divided by standard deviation of x plus some EPS. This is added such that even if the standard deviation is zero, we never have zero over here and it prevents exploding of our mechanism. Because neural network is nothing but just glorified multiplication and addition, and how you train them is through differentiation. That's it. That's all your neural networks are. Whole a mess of multiplication, addition, and differentiation. Okay, so the people who skipped maths in 11th and 12th, I'm sorry. Okay, so essentially what happens is you get the mean of each row, right? Then you basically you plug it this into the formula and you get your new values over here. And now you have normalized all of your features. So why even normalize it? Since I mentioned that it's a nothing but multiplication over here. So normalization actually takes, so suppose our input distribution of these weights was like this. But during training, it can so happen that with the various batches, it can start to skew. And the neural networks all works on continuous value or probability distribution. So if the distribution of the batches is changing over time, then the model will get lost or get stuck again and it might not even be able to train or get at a optimal minimum, right? So let's just look at it. So actually what's happening over here is the values are skewing, right? So when you multiply something big, 0.1, you get something big. But if you oversee over here, most of our values are between 0 and 1. And when you multiply values which are 0, between 0 and 0.1, they just keep getting smaller and smaller. And when you multiply values which are bigger than 1, they just keep getting bigger and bigger. The term for this phenomena is called as internal covariate shift, and this thing leads us to exploding gradients, and this thing leads us to underflow or vanishing gradients. So we prevent the problem of vanishing and exploding gradients. The main feature, actually there are other several reasons as well, but the main feature is it prevents vanishing and exploding gradients, and it just leaves you the headache of debugging your entire architecture. You don't have to worry that much about all of these problems now. So with the power of layer normalization and this residual connection, we are able to take care of these phenomena, right? So now what is left in the transformers module? Yeah. So essentially now you have done normalization also. Then it goes into your feed forward network. So this is just like Apple saying HD Retina display when it is just a 720p display. So what this essentially is, it's just your same dense layers. So dense layer, ReLU, this is your activation, and then again dense layer. So in our case, our sequence of length 7 by 5, right? So you pass it to a dense layer which might be of size 5 cross 2048, and then you pass it through ReLU, which gives its non-linearity, and this non-linearity is what allows it to bend the function to basically able to fit to anything that is out there, any target value that we want. Then it again goes back to something called something of 248 by this thing 5. So the final output is again 7 cross 5 only in lieu of these matrix multiplications. Then you again do the same residual connection with layer norm, and with this your encoder is complete. The entire encoder architecture is complete. Just let me just clear it so that it is visible. Yeah, with this your with this your entire encoder architecture is complete over here, right? And you can see this nx is over here. So in transformers, what they do is they basically stack these encoders n times, and this n can be dependent upon various features. So like your problem, how difficult the problem is, how much GPU memory you have, and where how much speed that you want, and Falana and Tingana. So these are all the factors where this n can depend upon. So you just stack it, and every time the output will be 7 cross 5 at the end, where for each word it is embedded into 5 dimensions. And that's how, from the transformers, you get all of your word embeddings through all of this glorified, glorified multiplication and addition and differentiation. Cool. So let me just erase all of this again. The decoder side of thing is also very similar, with actually only two things being different. So for yeah, so first thing is this one, where you can see that the same input was being divided into three. Now you only get one input from here, and then it goes over here, and the rest two inputs you get from the encoder side of things. Okay, and this masked multi-headed attention. So let me just clear this again. So this attention over here is glorifiedly called as cross attention. Going again with copying apple, cross attention. Everything is same, formula is same. It's just that you get the keys and the values from here, and you get the question or whatever you think you want from the decoder itself. Right. So uh, in case of our dialog completer, all of this is encoded into 7 cross 5. This becomes our keys and the values. Then they are again multiplied by something. And the same story is repeated again. Boo, boring, boo. What is this behavior? Anyway, so the same story is repeated again. So if I told you the intuition is query is basically your question, right? What do I want from this key and value that I have, which is being embedded. So this sentence is being embedded as keys and values in shape 7 cross 5. It has its own 7 self attention. It knows the meaning. It knows everything. Now what's left is for our dialog completer, given the query that what should be the next word. So firstly, it is just the start of the sentence. So given this query and given this context of keys and values, what is the next word that you create or you generate? And then basically when you play the Game of Thrones, the code goes like you either win or die, right? So this is the context. You know that we are talking about Game of Thrones. You know this is the tokens that represents the famous coast by Cersei Lannister, and you know that it is then preceded by this. So first you give you your query, again you push it to this encoder, then the output u is then fed again back to this decoder over here. It's the decoder is a for loop. Yeah. the only for loop over here, the only sequential C over here is this decoder, right? So then you send in you have this context, you again get either, then win or die, and you keep doing it until you get a stop token, which you identified that this is my stop condition, which is generated after you have encoded, after you have decoded everything, right? So firstly, this is a for loop, but how do we implement this mask multi-headed engine? It's actually very, very, very simple. What you basically do, where is it? Oh, okay, yeah. What you basically do is, remember guys, we were doing key dot query transpose and softmax, right? This is the value, this is the function that we were using, and then this is the scale scores that we were getting. What you basically do is you just, over here it should be add, not multiply. You just add this mask to this, and then you basically get this values over here. So now in the first token, the transformer can only attend to itself. Then in this, when it has to predict either, it can attend to itself, and then you also along with the previous context, that is the context that we have given. Then in the third token it goes like this and it goes like this. However, this entire matrix is always computed, then you just add a mask after this is done. Once this mask is added, then you again matrix multiply it with values, right? And then you again get your 7 cross 5 thingy. So this is so we have covered everything in terms of modules of the transformer. Now it's just a matter of coding each block and then plugging them as the diagram. So if you just follow this diagram, you'll have your transformer. That's it. It's that simple. You don't, it's not, even LSTM is complicated than this. If you go ahead and try to implement it on your own, frankly, I've never been able to implement LSTM on my own. But this transformer, it is simple. It is very easy. It has transfer learning capabilities. It is a very general. It is a very general algorithm. Too general such that even this Chat GPT uses this decoder block only. Chat GPT is just a decoder, right? It's a decoder only block. You give. There are anyway. This is not a session about Chat GPT. So yeah, this was the entire uh, transformers architecture layer by layer. We went through the architecture. We covered why LSTM was not used. We went through the entire sequence journey. What happens? What is the intuition behind each and every block? Is there any question that you guys might have regarding this presentation?
Thanks, Abhinav, for that session. Leaders, the floor is open to you all. Any questions? You all might want to unmute yourselves or put it in the chat box as well.
Right. Till then, you guys can interrupt me. I'll just go over the applications of encoder and decoder. So, if you look at Bert or Roberta, what they are your encoder only model, wherein they only utilize the encoder stack of the transformer and nothing else. So, encoder is something that is converting your x into x prime, right? And how it is doing? It is doing that by self attention. So via self-attention, what we know is we know about the meaning of each token, meaning of token, and we know about the position, and we know about the dependence of each token. So with this information, what all can we do? Right? With this information, what all are the applications that we can do? We can do question answering since we know about each token and their dependence. We can do name entity recognition. Name entity recognition is nothing but For a given token, you classify if it's a person or anything that you might desire. It's a token classification kind of thing. So we know the meaning of each token and the position. We can do NER. We know the meaning, the position, and the dependency. We can do relation extraction. We know the meaning of each token. We can pool them up and we can do text similarity. Again, we know the meaning of each token and the position and the dependence. We can also do sentiment analysis also, right? So these are just a few applications of your encoder. And in terms of decoder, decoder is all generative model. You guys already know about Chat GPT. It does all of this and much more, but it just need an encoder, right? Once you are able to encode something, everything is game for this decoder. You just have to train it on millions of documents. That's it. Everything rest is very easy. Yeah, yeah, that's it, everyone. Thank you for your time. If you guys have any questions, you are feel free to ask any of them.
Great. Thank you, Abhinav. Leaders, any questions? You might want to use the chat box or you can unmute yourself and put forth your questions. All right, Abhinav, I don't see any questions coming in. So, with your permission, if we can call it a day.
Yeah, yeah, sure.
Great. Thank you once again, Abhinav, for making such complex topics so simple for us. I love the way you put up your presentation, the first slide and the last slide, especially the transformer that you started off with and the transformer you ended with, and the way you put forward your content, making complex topics really simple for all of us, the sequence journey, the architecture, and all of that. So, thank you once again for this delightful journey. And I would like to thank all the leaders as well for joining us today. We shall be coming up with many more sessions forward. And I request all the leaders to please join us the same way. And in case leaders, you'll have any further questions, you all can reach out to Abhinav via Teams or he sits on the fourth floor. So he's always available to take up questions. So if in case you have any questions after the session, you might put forth to Abhinav directly. Thank you, Abhinav. Thank you, leaders, for joining us. With this, we shall be closing the session. But before we call it a day, I request all the leaders to provide the feedback using the LMS link mentioned in the chat box. Please provide your valuable feedback, which will help us make our sessions more impactful for all of you. Thank you, leaders. Thank you, Abhinav, very much. Have an amazing day ahead.
Thank you, Suman. Thank you, everyone. Bye bye.